Hello, vintage computer friends. We are not done yet with our 1983 Kosmos CP1 educational computer, and in this video I'm going to show you how to implement a recursive version of the summation program that adds the first n natural numbers, right? And in the previous two videos where I implemented this on the CP1 as well as on the Bush Microtronic, we just implemented an iterative version using a simple loop with two variables, right? One variable for the counter and one variable for the sum computed so far. And now I'm going to implement a recursive version both for the CP1 as well as for the Microtronic. And so we might want to start by reminding ourselves how a recursive version of the sigma I program, the summation program, could look like, right? So here's a Python-like definition. So we are defining a function sum, which takes one argument n, right? And now there's a case analysis. So if n equals 0, then this is the base case of the recursion, right? Then you're already done. You return the value 0, right? Else, it's divide et impera, as my old late computer science professor, Professor Schäfer, used to say. So we have to break down the problem into a smaller version of itself and then call the sum function recursively, right? So in order to compute the sum of up to n, we can compute the sum of up to n minus 1, right? And so this is a breakdown into a smaller part of the program, right? So a recursive call with n minus 1. And then when that returns, we of course have that result. We only need to add n in order to get the real result, right, for our invocation of the sum function for n. And yeah, tricky point of course is if you implement it like this, it's not, as we say, end recursive, right? You cannot simply transform this into a loop, because after the recursive call you still have to do something, right? So, and that means you cannot simply use a single variable, memory location or register for this n and the sum, because otherwise in the recursive invocations these register values or memory locations would keep overriding each other's, right? So you would lose track of your values. Instead, what programming languages use that support recursion, which is of course almost all of them, right? You use a stack, and this is what we are going to do, right? We are implementing a stack for the values, right? For the stack frames for the n local variable, as well as a return stack, which is necessary because if you now return recursively here, right? You gotta know where to resume basically your computation, and that's basically at an address in the calling function, right? So which is basically at this point here, right? So, and I mean in this case it's always going to be the same return address, but we are doing it in a general way, so we are implementing a proper return stack here. So, and interestingly, the CP1 does not really have native stack support in its instruction set, but we can implement one, because as I mentioned in my previous video about the CP1 supports indirect addressing as well as indirect jumping, and this is basically what we are going to use. So we are setting aside two memory cells which are now not storing values but addresses, right? And it's basically the analog of C pointers, right? So we need a return stack pointer, and we put this at memory cell 64, and then it basically points to the beginning of the return stack, right? So 080 is now the address for the region where the return stack starts, and here it's illustrated, right? So it just keeps growing down, 80, 81, 82, and it will contain the addresses of the where to return to, right? To the previous invocation, right, where the recursive call was made. And similarly, and more importantly in this example, we need a value stack, right? So a stack that keeps track of the n local variable, 3 to 1, right? Starting at address 100, 101, 102. And this value stack pointer we are storing at memory cell 65, and it contains the start address of the value stack. So, and we are now going to see how we can implement this on the CP1 using its indirect addressing modes and indirect branching instruction. And I already entered this program here, right? So And I'm going to go through a symbolic version, assembler listing basically, which contains mnemonic labels here, right, for the addresses, right, because it's just easier to follow through. So let's start at address 01, and I show you the program. So first we got to load, basically now prepare the stack pointers. First we prepare the return stack pointer, and I said that the return stack starts at address 80, right? So we used this instruction before. This loads a constant, in this case the address 080, into the accumulator. And now we are going to store this 80 address into the return stack pointer memory cell, right? And I said I set aside a memory cell for this, and you can see here, right? So it's at address 64, the return stack pointer, and it contains then the address of the return stack. So 06 means store accumulator content at this given address, right? So, and we do the same for the value stack, and I said the value stack starts at address 100, right? And that the value stack pointer is at address 65. And so same thing, right? So we are storing the value stack pointer start address at address 65. And now we are basically preparing the first recursive call, right? Because you got to call the sum function with your argument. And let's not do it for 3, but let's do it for 10, right? And the result should be 55. So we are loading 10 in the accumulator. And then we are using the first new instruction now, which is basically store indirectly, right? And rather than now storing the n argument 10 into the memory cell 65, right? Which would be wrong, because this is basically the stack pointer, right? So it should contain an address, but not the start n argument, right? So rather what 20 now does is it fetches, it stores basically the accumulator value 10 into the address cell whose address is given at the stack pointer position 65, right? So it dereferences first the address, and then it basically puts 10 into this memory cell 100, right? Because this is where the value stack starts, right? So we now have the first n argument 10 on the top of the value stack, right? In the first stack frame, if you like. So we now also need to prepare the return stack, right? And interestingly, the return address basically after the recursive call is where the program basically continues and simply displays the result on the display is also address 10, right? So here's another 10 basically, and this 10 is basically the return address, right? The end label here, right? Which is at address 10, and we are putting this now on the return stack as a first value, right? And again, we are using indirect addressing, but as I said, the return stack pointer is at address 64. So value stack pointer is at address 65 and return stack pointer is at address 64. So we have now basically prepared our recursive call, and we can now make the call to the sum function, right? Given that we have the stack frames prepared. And the sum function starts at address 17, so 09 is just an unconditional branch, a goto, right? And then, so we are now at address 10, so this is basically after the result has been computed, right? So, and all we got to do is load basically the return value, and we are setting aside one more memory cell which contains the return value. And this is at address 62, right? So this is the return value label. So this is basically just to pass the latest result back to the calling function, right? And then we are using the display instruction 02. And rather than using the wait instruction, we are now looping, right? So it's an endless loop. It keeps displaying the value on the display until we hit the stop button. So that's an endless loop. So now there's a little bit of empty, right? But we are now, because I had a previous different version of the code there, but we are now ready to start the definition of the function, actually, of the sum function, right? And it starts at address 17, right? So let's continue here. So first we now do the conditional, right? We got to check if the current n value is 0, but for this we first need to load it now, and rather loading it directly now from a memory cell, we have to load it indirectly, right? So this is what we have to use the stack for now, the value stack. So previously we would use something like 0, 5 and load address, right? Specify the address directly. But now we are loading from the DB reference stack pointer. So 19 means load basically from the address that is specified in this memory location. And 6 to 5 is of course this stack pointer, the value stack pointer, and it points to either of these now, 100, 101, 102, depending on how deep we are in the nesting of the recursive calls, right? And it loads the appropriate n value now. So now we have the n value from the value stack in memory, right? In the accumulator, sorry. And we are going to check if it's 0, right? So at address 60, we have set aside a 0 constant, right? As I said, for comparisons, you cannot use immediate operands in the comparison opcode 10, right? But you got to specify a memory cell again. So 60 contains 0. So if the accumulator and hence the n value, the stack frame value stack frame value is 0, then basically we branch, right? So this is branch if equal 11, and the address is the bottom case of the recursion, right? Which is at address 46. And good, but so now we are at the point here where this is the inductive case, right? So n is not 0, we did not branch, and now we got to do something, right? So first we need to compute n minus 1. First we need to load the n value from the stack again, right? And we want to subtract 1 now. Basically we want to prepare the recursive call to the sum function. And for this we set aside another memory cell which contains the 1 constant, right? And then subtract 0.8 from the accumulator. 0.8 is the subtract opcode. So now we have n minus 1 in the accumulator. And we also have to store this back into a memory location. And for this I'm using yet another memory location, the aux, an auxiliary memory location, right? Just to keep track of, temporary results. So I'm storing n minus 1 at address 63, which is this aux value here. And now we basically have to prepare the recursive call sum n minus 1, right? We have already computed n minus 1 and stored it in the aux memory cell, right? And now we have to create a new stack frame, basically a value stack frame for this recursive call. And to do so, we now first load our value stack pointer. So, and we add 1 to it, right? So basically what we do is we have to increment the address here in the value stack pointer, right? So we load this directly now from address 65, it's 100, and we add 1 to it, right? So 101, so we basically move the stack pointer to the next address here, right? And this is what I call, we create a new value stack frame. So we are adding 1 to this address, right? And then we store it back basically, right? Directly in the value stack pointer memory cell. So the value stack pointer has been updated now and points to the next value stack frame. So, and now we also have to, in this new stack frame, we have now make sure that the n minus 1 value is being found there, right? So basically this is passing in the argument into the recursive call, right? We already created the stack frame, the value stack frame. Now remember, we stored this in the auxiliary memory value n minus 1, right? So we are loading it from there into the accumulator, and then we are dereferencing the stack pointer, the value stack pointer, right? And 20 means, dereference and store at that address, right? So that means we are now storing our argument basically, and let's say we did the invocation with 10 like in the program, right? So we updated the stack pointer to 101, and now we are storing 9 here, right? So this is what this instruction does. So yeah, and now we are basically ready to do the almost ready to do the recursive call, but we gotta do one more thing, and this is we have to set up the return stack. So we also need to increment basically create a new return stack value in the same manner, right? So we add 1 to this address here in the return stack pointer, and so then it points to 81, right? And then we also need to basically store the return address in the new return stack frame, right? So same thing. So load the return stack pointer, so the address, right? Add 1 and store it back, right? At 64 is where the return stack pointer is. Yeah, we are now ready to basically put the label in there, right? So now we have the new return stack frame, but we also need to put in the return address. And if you look at the code here, right, so the recursive call is at address 33, and at 34 is where it needs to continue, right? So this label 1 is at address 34, so we load this as a constant into the accumulator, and then we are using store indirectly, right? Dereference the return stack pointer and store it in the frame there as a return address. Yeah, and now comes the recursive call, and we already know that the sum program starts at address 17, so this is just an unconditional branch to that address, right? So, and now we returned basically, right, from the recursive call, and let's continue here. So what do we have to do after the recursive call? If we look at the program again, we know that we now are at this point here, right? We returned, and with the results that we retrieved, we still have to add n, right? This is what's left to do, and then return again. So let's see how we implement this. So again, of course, we need the value stack pointer, right? And now we gotta basically pop the frames, right? So because we created frames, right, and added ones basically to the stack pointers, right, to point to these new frames. But after the recursive call, we also need to decrement and basically remove these pointers so that they point back to the previous stack frames, right? So it's push and pop, right, of these value and return stack of stacks. And so we are going to basically pop now, remove the value stack frame, and for this we are decrementing the address of the value stack pointer using 08 and the 1 constant in 61. We updated it again and store it back, and we also pop now the value stack, which is at the stack pointer, the value stack pointer is at 64, we subtract 1, and we store it back, right? And again, you see very nicely this von Neumann bottleneck, right? Load, do arithmetics in the accumulator, store back. Always 3 instructions for each atomic update operation of a cell, basically, right? Which is not atomic, but it could be atomic, right? Like in the microtronic, it's only 1 instruction to do this kind of thing. So the programs tend to be longer and more complicated on the CP1. But then the microtronic does not offer indirect addresses. But check out my next video where I'm going to show you how to emulate basically indirect addressing and indirect branching on the microtronic, and I'll also have a recursive version of this summation program on the microtronic. Eventually I'll show you how to implement towers of Hanoi, which is a nice, textbook example of recursion that every computer science student in the first semester, of course, learns. Okay, so we popped the value and the return stack, and now all that's left to do is basically do the addition, right? So for that we are going to load the current n value, and we are this is now n, not n minus 1, right? But remember that we stored the result in a special return value register, right? So what sum n minus 1 returned is in this return value memory cell at address 62. So we can simply use add now 07, add the accumulator, which has been loaded with the current n value, to the result of sum n minus 1. And then we are also storing this back in our special return value memory cell 62, right? Again, load, arithmetic, store. Okay, and now we are basically ready to return from the recursive call. And for this, we are using another load indirect, right? So we are loading the return address now by dereferencing the return stack pointer. And now what we want to do is, now we have the return address in the accumulator, right? But in order to do a jump now to this return address, we cannot use the address that's stored in the accumulator, but we have to store it in another memory cell, right? And for this, I'm using the aux memory cell, right, 63. So I'm storing the return address that we fetched from the return stack, right, over the return stack pointer into this aux register. And then I'm using a new instruction here, the first time we encounter this, and this is branch indirectly, right? And what that does is now it fetches the address that is stored at this address, right, which is the aux memory cell, and jumps to this, right? So basically we now are executing a jump to the return address, right, which is has been fetched from the return stack over the return stack pointer, and which has been stored in this aux memory cell at address 63. So yeah, we have just computed our recursive call and returned from the non-base case, right? But now we still have to implement the base case, and this starts here. And remember, the base case is that n is 0, right? And all we have to do is we load the result 0 into the accumulator. And again, we have to, we agreed that we are using this this return value memory cell at address 62. So we are storing the 0 there. And again, we need to prepare a recursive return from the recursive call now, right? And again, we are dereferencing the return stack pointer. We are putting this into the aux memory cell, and then we are branching indirectly, right? So we also returned now from the base case, so which is of course here, right? So this is this return we have implemented now. Yeah, now we are done with the implementation of the function, and all that's left to do is basically put the data constants into the data region, right? And as I said, we set aside a couple of memory cells. So at 60, we want to have the 0 constant, right, for the comparison if n equals 0. At 61, we have a 1 constant, right, so to add or subtract 1 for the stack pointers, right. Then here, this is the memory cell which already has a value because I ran the program before, but this is a return value, right, memory cell. Here we have the, oops, sorry. So here we have the auxiliary value, right, which also contains the value because I ran it before. And then at address 64 is a return stack pointer, right, and here is a value stack pointer, and addresses 80 and 100, right. Yeah, so we are now good to run the program, and remember that I put in 10 basically for the argument, right. All we got to do is load the start address into the program counter and hit run. And there we go. 55 is the right answer for 10, right? And now it's doing this endless loop for the display, right? It's not using the delay operation, so I have to use the stop button for the first time here. Let's say 04012. And I mean, of course, I could simply check how much frames we have, right? How many? And that still works, 78, right? Alright guys, so that's it for today. Please stay tuned for the next video where I'm going to implement a similar version, a recursive version of the summation program on the microtronic. And that's going to be also interesting, I think, because the microtronic does not offer indirect addressing or indirect branching, but I found a way to emulate this, so it is a proper recursive implementation. And then eventually we are aiming for the towers of Hanoi on both machines. Until then, thanks for watching and stay tuned.